Welcome to the Explainer. So, if you've studied materials science, you already know the deal with dislocation slip, right? It's the standard way crystals permanently change shape under stress. But what happens when those normal rules just completely break down? What does a material actually do when it simply cannot slip? Well, today, we're looking beyond the basics to see exactly how crystalline lattices accommodate stress when their primary path is completely blocked off. Let's dive in.
Here's our roadmap for today. We'll quickly cover what happens when slip is constrained, then explore stress-induced martensite, macroscopic kinking, the core principles of twinning, environmental triggers, and finally, we'll synthesize slip and twinning. Let's get started.
All right, part 1. When slip is constrained.
Think of dislocation slip as the path of least resistance, right up until it isn't. When a crystalline lattice faces some extreme constraints, like, say, exceptionally low temperatures, tricky geometric limitations, or incredibly high strain rates, dislocation motion becomes energetically unfavorable. Basically, it's blocked. But the material still has to yield to that applied stress, right? So this triggers 3 critical backup plans: stress-induced martensite transformations, macroscopic kinking, and deformation twinning. Let's move to our first mechanism and see how this plays out.
Moving on to part 2, stress-induced martensite transformations. So instead of a standard dislocation just sliding through the lattice, the parent material handles the stress by generating a specifically sheared region. It's not just movement, it's a total structural identity change. The lattice distorts abruptly into an entirely different phase. We actually observe this structural shift across a variety of lattices. For example, in carbon steel, we see a shift from face-centered cubic right over to body-centered tetragonal. In titanium alloys, it moves from BCC to HCP. We even see it happen in ceramics like zirconia, snapping from a tetragonal to a monoclinic phase.
Now, why does this actually matter for materials engineering? Well, it's honestly fascinating. This phase transformation fundamentally alters the mechanical profile of the material through what we call the trip effect, transformation-induced plasticity. Because the metastable austenite transforms into martensite right during the deformation process, and because martensite inherently possesses a much higher work-hardening rate, the macroscopic result is incredible. The material suddenly exhibits a higher strain hardening exponent, a higher ultimate tensile strength, and far greater uniform elongation. The deformation itself literally makes the material dynamically stronger.
Okay, part 3, macroscopic kinking mechanics. Now, it's absolutely crucial we separate this from the atomic-level dislocation kinking you might already know. Macroscopic kinking happens in materials that lack resolved shear stress. Instead of sliding, the crystal structure undergoes a highly localized slip that causes this distinct symmetrical buckling. It is a macromechanical deformation band that can form under both compressive and tensile loading conditions, physically bending the lattice at these incredibly sharp angles.
So, the real name of the game here is geometry. Kinking doesn't just happen randomly anywhere. It's highly orientation dependent. The kink band neatly aligns right on the slip plane to maintain perfect structural symmetry. We systematically see this triggered in hexagonal close-packed or HCP metals. When a single set of basal planes is oriented nearly perpendicular to a tensile axis or parallel to a compressive one, the lattice simply cannot resolve the shear stress for normal slip. So what does it do? It accommodates the deformation by forcing everything into an exceedingly narrow buckled band.
Next up, part 4, principles of deformation twinning.
Deformation twinning, often called mechanical twinning, is pretty much universally recognized as the second most critical plastic deformation mechanism right after dislocation slip. But the mechanics? Totally different. Instead of a dislocation gliding atom by atom, the lattice inside a specific volume element undergoes this uniform shear strain. This displacement shifts the entire region so that it orients itself as a literal mirror image of the parent lattice, reflected perfectly across what we call the twin boundary.
Every crystal structure has a specific set of twinning elements. In twinning, the resultant twin shifts a precise, uniform fraction of an atomic distance from one plane to the next. This is perfectly quantified by a mathematical model, relating the shear strain directly to the atomic spacing and angle. It's a highly ordered, mathematically predictable shearing that completely reorients the lattice in one swift, coordinated movement.
All right, part 5, environmental and structural triggers.
So here's your environmental trigger dashboard.
The absolute golden rule here is that twinning acts as the dominant mode when the critical resolved shear stress needed for standard slip shoots through the roof. Think about it. Dislocation motion is highly thermally activated. It relies on temperature. But the stress required to nucleate a twin? That's largely independent of temperature. Because of this, twinning easily overrides standard slip at very low temperatures or under extremely high ballistic strain rates. Think of a bullet impact, where dislocations simply don't have the time or the thermal energy to get moving.
But hey, it's not just about the outside environment. The internal architecture plays a massive role too. Fundamental unit cell dimensions absolutely dictate a material's mechanical response. In hexagonal close-packed structures, the probability of twinning is directly tied to the C/A ratio. If that ratio is particularly high, specifically anything greater than 1.73, the physical dimensions inherently restrict certain primary slip systems. The material is essentially mathematically forced to rely on a combination of basal slip and twinning just to accommodate the deformation without fracturing outright.
We can also trace this directly back to stacking fault energy, or SFE. There is a very precise mechanical domino effect happening here. When a material has lower SFE, stacking faults form much more easily. This actively suppresses the cross-slip of dislocations, and because they can't cross-slip, planar slip takes over as dominant. That rapidly generates higher flow stress. And once that flow stress crosses a certain critical threshold, boom, twinning is actively promoted as the brand new path of least resistance.
And you should know this shift to twinning, it isn't some slow, gradual process. It is sudden. In mechanical testing, this rapid nucleation leaves a really clear footprint. If you look at a stress-strain curve for something like a cadmium sample, you won't see a smooth plastic curve. Instead, twin formation shows up as measurable, distinct, serrated yielding. To stress builds, a twin violently nucleates and shears, which drops the stress, and then the cycle repeats. That's what causes those sharp, jagged peaks and valleys.
And when I say violent, I mean that literally. Deformation twins propagate at just immense velocities, sometimes approaching the speed of sound inside the material itself. Because it happens so incredibly fast, the material literally screams. It produces an audible cry. The most famous example of this is the tin cry. It's this distinct cracking, tearing sound you can actually hear with your own ears, just by bending a piece of polycrystalline tin. That sound, that is millions of atoms violently twinning all at once. It's wild.
Finally, Part 6, Synthesizing Slip and Twinning.
Synthesizing these mechanisms really highlights their fundamental mechanical differences. Look at slip. It happens in full atomic distances, it can move in both directions, and it completely preserves the crystal orientation. Twinning, on the other hand, is unidirectional, happens in precise fractional distances, and completely changes the crystal orientation into a mirror image. But here is the most critical difference to remember. For slip, the stress needed to cause yielding is actually lower than the stress needed to continue flowing. Twinning is the exact opposite. The massive stress required to nucleate the twin in the first place is far greater than the stress required to actually grow or move it.
Which brings us to the ultimate insight, and really the main thing you should take away from this explainer today. On its own, twinning actually provides relatively minimal raw plastic deformation compared to just standard slip. So why do we even care? Well, because of its absolutely critical secondary function. By rotating the crystal lattice into a mirror image, a twin fundamentally alters the local Schmidt factor. It takes lattice planes that were previously exhausted or just oriented terribly for slip and forcefully rotates them into favorable positions. It literally unlocks them, enabling further slip to continue. This leaves us with a pretty provocative thought. If we can intentionally engineer our alloys to leverage this exact reorientation, how much further could we push the absolute boundaries of structural materials? Thank you so much for exploring this with me today.